Hello, everyone. Welcome back. Today is December 28th, 2024. I'm making this recording in Waikiki, Honolulu, Hawaii. I wish everybody a happy new year. All the best in 2025. Today, we are going to talk about lecture 7. On Hillert non-equilibrium thermodynamics, internal and external variables, internal processes in homogeneous systems. As a first review, the combined laws we have talked about. This is the equation in terms of internal energy for the combined law. du equal to dq plus dw plus summation of ui dni. If we consider only the hydrostatic pressure, then the dw becomes minus p dv. And in this equation, I showed the ui in the red color. This term was introduced by me in 2020 in this paper. In 2016, I introduced this equation for the entropy change of a system. ds equal to dq over t, that's just the heat, that's we call it Clausius entropy change, and plus summation of SI dni plus dips. And again, SI, this term was introduced in 2016 in my book, together with Dr. Yi Wang. The dips here it's very important, as we can see later, was introduced by Hillert, or Hillert-Kipling's equation. So by combining these two equations, we got the combined law. One of the most important outcomes of defining UI and SI is that now we can define the chemical potential. This equation again was presented in 2020 in the paper shown on the left QR code here. UI, mu I equal to UI minus TSI. Again, the UI is a partial internal energy, SI is a partial entropy of component I. Consequently, we got the combined law in terms of internal energy. du equal to TdS minus BdV plus summation of mu I, the mu I is chemical potential, dni minus T dips, which is entropy production due to internal processes. And the Hillert did another thing that he put all these terms before the T dips into one summation called YA dxa. So this is significant because it, as shown in the next few slides, it separates the internal variable, external variable, potential, and molar quantities. As we mentioned before, we should avoid use the extensive variable, intensive variable, as again it will be shown here. It will be shown here very clearly why that's important. Now let's see what the Hillert non-equilibrium thermodynamics is about. So the key thing Hillert did, of course, also by some scientists did it before him, is to keep this term. It's dj d psi j, which these are the many internal processes, right? Summation of it in the combined law. So that's very important because now you see this entropy production due to the internal processes, which means which indicates the system is in non-equilibrium state. So in this equation is so important, it integrates equilibrium and non-equilibrium thermodynamics together. So put the both of them on the same foot. So they're not separate anymore, because I really think before Hillert systematically put them together during his teaching for many years at the KTH, they're separate, right? You have the non-equilibrium, the equilibrium thermodynamics, but this equation really put them together on the same foot. So that's why I think it's justifiable. It's justified to call this Hillert non-equilibrium thermodynamics. Again, we always remember that it's not just by a single person. There are a lot of research and study before that, but Hillert was the person really systemizing in his book, in his teaching, and his books. So now, of course, we can extend this to beyond internal energy. We can do enthalpy. Now, basically change the V and P. Make minus P to be the natural variables of enthalpy. But again, we keep this enthalpy production term. Now, as we did before, we can do Helmholtz energy. We change S and T in the combined law. Again, we keep this internal entropy production term. And the Gibbs energy, as I mentioned before, that we can just define any free energy by switching the natural variables from molar quantity to potential. As you have, some of you learned before, as we show in next lecture, is that if you change all of them to a potential natural variables to be potentials, then you get a Gibbs-Helmholtz equation. And another very important thing in terms of the equation we have here is that what Hillert did was separate the external internal variables. That term is extremely important. Okay. So let's look at the equation, the combined law in terms of internal energy. As I mentioned it before, Hillert combined the first three terms into one summation YA dXA. So the YA is YA represents the potentials, XA represents molar quantities. So here, for example, YA would be temperature minus P chemical potential. We can also add electric field and magnetic field, so forth. If we go beyond the hydrostatic work, we can have the stress and the strains, right, given the strains. So the external variables are the variables which are independently controlled from outside, externally. Okay, so all the XA here are external variables for you, for the internal energy, because they are the natural variables of you. So in this equation, you can see here would be the entropy, volume, and the moles of each component. Okay. However, as we mentioned before, Ni, the moles of component S, are not independent. They are related to this equation. ds equal to d curve T plus the summation of Si dni and plus dips. As we just showed in the previous slide, we can switch natural variables. So we have when we do that, the natural variables become a combination of XA, molar quantities, and potentials. For example, if we do the Helmholtz energy, we'd have V, N, and T as external variables that we control from outside. And if for the Gibbs energy, we're going to have minus pressure, Ni, and T as natural variables. Now, these are very important for the Helmholtz energy and Gibbs energy. Now, temperature becomes the natural variable, so entropy becomes an independent variable, a dependent variable. Okay, so it's not independent anymore. So that actually simplifies the discussion, as we will see later. So what the internal variables are the variables inside the system. Okay, so they are all molar quantities. They're used to define or describe the states inside the system. Okay, now if we talk about the internal energy, in the literature we always call it ensembles, right? So we have V and IS as natural variables. We have one ensemble. If we have V and IT, we have another ensemble. So there are different names for that. So I'm not going through those names because I think they're sometimes a little bit confusing. Okay, so I would rather just use the variables directly. Okay, but however, the internal variables are not only those individual external variables we were talking about before, V and S, but can also be combinational. Particularly important is when we talk about chemical reactions. Chemical reactions means you have A plus B from C plus D. It involves many, many components. But it's very rare for us to talk about a combination of volume and Ni. Now we can do that too, as we show them in the future, talk about the internal processes. We actually realize that it could be useful. To combine those variables. For example, we talk about thermal diffusion. Thermal diffusion is the temperature-driven diffusion. Okay, all right. Again, if we have entropy as a variable, entropy is a variable. It's an independent or a dependent variable, but the entropy is always related to S, Ni. Okay, so that's a very important relation. Thermodynamics makes the description of a system much complicated, or the internal process much complicated because of this definition, or this relation between entropy and Ni. Okay, so then we talk about internal process, right? We now, you see, we defined the external variables, the internal variables, and then internal variables represent or describe the states of a system. So then the system can change from one state to another state. So that involves internal processes. So we talk about a system, okay? Particularly we talk about a homogeneous system. That means what I mean by homogeneous, that means all the molar quantity inside the system is the same is homogeneous in the system. And then this homogeneous system has some interaction with the surroundings. Okay? Based on the combined law for the internal energy, with all the dxa equals 0. That means there's no exchange of entropy, mass, and volume between the system and surroundings. However, it's very important to realize this is not an isolated system. If the system is non-equilibrium. Of course, as we show later, if it's an equilibrium system, then it's also an isolated system. So the reason is because the S and Ni are related. So this is definition of entropy change. So we get dq equal to TdS minus T dSi Ni. This is then total entropy change. The entropy change due to the mass change. This entropy reduction. Okay. Now you see the ds equal to 0, ENI equal to 0 from the definition we have there. So, but the T dips is not equal to 0 yet for non-equilibrium system. So that means the system must exchange heat with its surrounding. And then from the combined law, we find the du equal to dq because dw equal to 0, and there's no mass change. There's also one term left. So du equal to dq minus T dips, and so it's not equal to 0 either in general, right? Then we can identify. This can also obtain just directly go from the combined law. So okay, this du equal to ya dxa minus d summation of dj d cos ij. The dxa all equal to 0, so I have the second term left. So same equation here. Okay. So if we consider one internal process from a region 1 to region 2 in the system. Okay, so we have the d cos I here for region 1 to region 2 in the system. So we do a virtual experiment. You think about a virtual experiment, you move one molar quantity from one region to another region inside the system. And then come out the two types of equilibrium we can talk about. That was really, really elegantly discussed by Hillert, is that you have d dx equal to 0. If you d dx equal to 0, du equal to 0, right? So then the system is isolated. If du is not changing, so I have dq equal to 0 and the dw equal to 0, and the summation of mu I dni equals 0. Okay? So all equals 0, so it's isolated. It's an isolated system. However, for this because this is d times d cos I, it can be d is equal to 0 or less than equal to 0 because no driving force. So we call it equilibrium or smooth equilibrium. When equal to 0 is smooth equilibrium. It's less than equal to 0 is a sharp equilibrium. However, there's another situation. This d cos I equals 0. Is that even though d is larger than 0, that means there's driving force for that internal process. However, this doesn't happen because Dick cycle zero. So this is called freezing condition. Is connected freezing. For example, as we showed here, is that you cut off. There's no connection between these two. And it blocks connection. It blocks it because the barrier is too high. The barrier is too high. So basically, you increase the barrier to finish if you cut it off. So the one typical example is diamond and graphite, right? The driving force for diamond to become for diamond to become graphite, the driving force. However, it doesn't happen under normal condition because the barrier is too high. Okay, so it's kinetic limited. So here they call it a freeze-in condition. So it's also type of equilibrium, right? Because it does not produce entropy. So let's do some specific internal processes, S and V, okay, which move ds from region 1 to region 2, or dv from region 1 to region 2. Okay, look at a virtual experiment. Again, I like it very much because Hillert often use a virtual experiment to teach us to understand these abstract concepts in thermodynamics. So consider a virtual experiment with entropy change. We'll move some entropy from region 1 to region 2. So d psi equals to ds, okay, inside the system. So in du, so what change of the system of du? du equals to du1 because the region 1 has du change and the region 2 has du change. We'll add them together. So we take the entropy out of the region 1, so it's minus ds. So minus ds here, T1 minus ds2. The region, we don't know the temperature, right? Yet, what's that T1? Temperature region 1 minus times minus ds. The ds is positive, right? And then this region 2, region 2 here, we add entropy into it. So it's T2 ds. So we know this should be minus d ds, that's the internal process, d psi equal to ds here. So we get driving force equal to T1 minus T2. So the temperature at region 1 minus the temperature at region 2. The D equal to T1 minus T2. We know that if T1 is larger than T2, then the temperature at region 1 is higher than temperature at region 2, the D is larger than 0. So the driving force. So the entropy will flow from region 1 to region 2. It's very important, it's entropy flow, not heat flow. Okay. But of course, even we know that the entropy and the heat are related. But from the thermodynamics, from the combined law, it's really entropy flow, not the heat flow direct. Okay. Now, if there's no driving force, that means we get equilibrium. Equilibrium is that when T1 equals to T2, the two regions have the same temperature, there's no driving force, then du equals to 0. Okay, so that's the equilibrium condition. So we now know that if the system is at equilibrium, or the condition for the system to be at equilibrium is that a temperature to a potential, right? Temperature must be homogeneous. So that means the potential, temperature as a potential must be homogeneous. So we do another virtual experiment is move volume from region 1 to region 2, then d psi to dv. Again, dv is positive, right? Because d psi is positive, we represent a process. Okay. This time now we have the volume change, so the energy change from region 1 is minus P1, it's the pressure in the region 1 times minus dv because volume is decreasing from the region 1, and then the region 2 is minus P2 times dv. Okay, together is P1 minus P2 times dv, and equal to minus d dv. Okay, now we get the d equal to P2 minus P1. So now we can see that if P2 larger than P1, the d is larger than 0. That means region 2 has a higher pressure than region 1. That means then we're going to have the volume flow. Volume flows from region 1, which is low pressure, to region 2, which has higher pressure. So try to expand that volume in the region 2 so the pressure can decrease. So then at the end of the day, at the end of the process, you should reach equilibrium. So I actually would say at the beginning of for the system to be at equilibrium, the equilibrium conditions that P1 equal to P2, there's no driving force. Then du equals 0. So that means that internal process, if we move on from here to there, will not produce any entropy production, and then the internal doesn't change. So system is at equilibrium. So we got equilibrium condition now based on the two virtual experiments, the two potentials, temperature, pressure, both must be homogeneous in the system for equilibrium. Okay, now let's move the Ni, right? Move the component. But of course, we know already there's the issue because the volume, the mass, when you move the mass, you move the entropy at the same time. Okay. But you cannot keep the entropy the same. But volume you can do volume. We'll talk about later. You can do the volume. You can keep the volume same, right? And increase the pressure. Right. So do a virtual experiment is to move a component I from region 1 to region 2. So decosize the D and I. How about the relation between the D and I and the DS, as we mentioned many times already? That because it cannot be independently changed, so we have to change our function. So we use homogeneous energy instead. So dF equal to minus SDT is what I have here. So now we switch S and T. We keep everything the same here. So now I have TS in natural variable, right? Okay. So now condition with those are different now, right? We're going to do the natural variable. We keep the natural variables constant in this process. So, and the dT, constant temperature, constant volume. There's no temperature exchange, no volume exchange, no mass exchange between the system and surrounding. The internal homogeneous energy change will equal to summation of the entropy of reduction of all the independent internal process in the system. So if we do that one, do the internal, again, now we do the internal process to move the component I from region 1 to region 2, D and I, and this condition, which is no exchange of mass, no exchange of volume between the system and the surrounding, and the temperature are the same between the system and the surroundings. We get this change. This internal process will change the internal homogeneous energy like this. Will be mu I at the position 2 minus the mu I at region 1, and equal to D and I. Then we can immediately define the D equal to mu, the chemical potential component I at region 2, 1 minus the chemical potential of component I at region 2. Okay, so this is the chemical potential at region 1 minus at region 2. So now we see that if this chemical potential at region 1 is higher than at region 2, they have a driving force for the component I to move from region 1 to region 2. Okay, so you're going to have flow, mass transfer. So if the two regions have the same chemical potential for that component, there'll be no driving force. Okay, then system at equilibrium. So we get equilibrium condition now. Now you see for 3 sets of the potentials, through this virtual experiments, we have identified that the equilibrium condition for the system is that all the potentials are homogeneous. Temperature is the same everywhere, pressure is the same everywhere, but the chemical potential of each component is the same everywhere. It's homogeneous, so all of them are homogeneous. However, remember that when we move the mass, they have this in virtual experiment for the component I move from region 1 to region 2. We found that we also move the entropy, right? You want to keep the temperature same everywhere, we have to move entropy too. Okay, so by putting that equation, by putting the equation of entropy and the heat together, because dT equal to 0, ds must be equal to 0. Okay, so there must be heat transfer from region 2 to region 1. Okay, so you must balance the entropy change due to the mass transport. So that means it's reverse heat transport from the region 2 to region 1. So the entropy of the system is the same everywhere, and the temperature is the same everywhere. All right. Thanks, everyone. Now finish lecture 7. We're going to lecture 8 in next recording. Thank you.